Hello everyone, welcome to this video. In this video we shall be looking at the geometrical significance of differential equations and their solutions, right? So you already know what is a differential equation, what is the general form of this differential equation, and how does the solution of this differential equation, right? You know how does it look like mathematically. Now let's see what do they represent when we talk about the geometric significance of these two, the differential equations and their solutions, right? So when we are talking about geometric significance, so we wanted to visualize what does this mean graphically, right? So for that, if we go back to what we have previously studied about functions, so you know any real function that may be represented geometrically by a curve in the xy plane, correct? So you have some x and y plane, so you have some curve, this is represented by some real function f of x, correct? So this is the curve, and you also know that if you take the derivative of this particular function, which is f prime x or f dash x, whatever you like to call it, this derivative of f at x, this is represented as the slope of this curve, whatever is this curve which you have drawn. So if you take some point here and if you draw a tangent to this curve at this point, then this tangent would give you the slope of this curve at this point, and this slope is given by f dash x, right? This curve, another curve. So what does this general first order differential equation represent? So if you remember, first order differential equation in the simplest form could be written like this: dy by dx is equal to some function of both x and y, correct? Where what is this function f, small f, that is some real function, right? And this function now represents geometrically the slope of this function f of x at every point x and y at which this function is defined. Why? Because here this function f of x y is written in terms of dy by dx, and dy by dx is what? It is the derivative of y at x, correct? So therefore it represents change in some quantity y, so it give you the slope of this quantity y, correct? So if we assume that this differential equation, now once you know that this differential equation, here in this differential equation this function small f represents the slope of the given function. So here for this differential equation we have one parameter family of solutions, right? And so we assume that what is the solution of this differential equation? Let the solution be small y is equal to capital F x comma c, right? So here instead of y we have this parameter c, where what is c? C is constant, correct? So we have this as the parameter. So once you solve this differential equation, dy by dx is equal to small f of x y, so by the most common method, which is integration, say, then you obtain the curve of this kind: y is equal to capital F x comma c, right, where c is the parameter. So what does this solution represents geometrically? This solution represents also, because on changing the value of c you get another solution which is also a solution, correct? So therefore here you have many solutions, and in fact a family of solutions. So each solution would represent a curve. So a family of solution would represent family of curves here on the xy plane. So this one parameter family of solutions represent one parameter family of curves in the xy plane. So basically in the xy plane, as many solutions you have, those many curves you will draw, correct? So all of these curves, they would give you the solution to your differential equation, and your differential equation would tell you the slope of all these curves, correct? So this is the significance. So, and moreover, the graph of the solutions of differential equation, they are also called integral curves. Why? Because the solutions, the integral curves, they are obtained by integrating your differential equation. So basically we wanted to get rid of this differential here, right? So this is done by the basic method of integration, correct? So why they are called integral? Because the solution curves, they are obtained after performing integration of the given differential equation in most of the cases, correct? So let's see this concept of through an example where we wanted to represent some differential equation and its solutions. So here we consider the first order differential equation dy by dx is equal to 2x. Right, this is a differential equation. Now we say this differential equation defines the slope 2x at the point where we have coordinates x comma y for every real value of x. So here for this particular case, the solution of this differential equation, that is a one parameter family of solutions. Now once you differentiate this or you substitute this solution into your differential equation, so when you differentiate it, you get 2x only. dy by dx is equal to 2x. Why? Because c is a constant, so dc upon dx is going to be just equal to 0 because c is a constant. So it satisfies your differential equation, and you can take the value of c as anything, 1 2 3 4 5 6 and so on. You can take any value of c. So for different values of c you get the different answer. For example, when you get c is equal to 0, you get this curve. For c is equal to 0, you have y is equal to x square as this curve, right? So here you see, what is this? Y is equal to x square. This is a parabola. Similarly, y is equal to x square plus c is another family of parabola where each parabola is now displaced by c units. If it is plus c, it would be shifted upwards. If it is minus c, it would be shifted downwards, correct? So this represents the solution of differential equation, and you see there is not just one solution for this differential equation. There are many, in fact a family of solutions present here, right? So all of them, they represent the parabolas. Thus the family of parabolas y is equal to x square plus c defined by this differential equation dy by dx is equal to 2x is that family of parabola in which we have the slope as 2x given at the point x comma y for every real value of x. And in fact these parabolas, they are the integral curves of your given differential equation dy by dx is equal to 2x, correct? So I hope you understood this concept well. Well, that is it for this video. Thank you for watching.